Section 15 is on analysis of categorical data using the chi-squared test. So the chi is Greek letter X, that's a capital X, and it's squared, so they call it chi-squared. And it's used for analyzing variation, essentially. So chi-squared is defined to be this. So we did not cover this in chapter 10 because we really just didn't need it until now to analyze the categorical stuff. And it is, you'll recognize this, it is n minus 1 in the sample size, of course, times s squared, which is the sample standard deviation, over, s is, and then over sigma squared, the actual. Okay, so that is called a chi-squared variable and has a sampling distribution called the chi-squared probability distribution. So it's called the chi-squared variable and has a sampling distribution, right? If you did multiple samples, just like on sampling means and things like that, sampling distribution called the chi-squared probability distribution. Chi-squared probability distribution with n minus 1 degrees of freedom. So degrees of freedom is equal to n minus 1. Generally, will help you keep track of degrees of freedom, and it gets strange in the next one I'll show you. First, let's go over this example that in concept before we get into the categorical stuff. So this test statistic is used to make inferences about a population variance and therefore a population standard deviation. So it really goes hand in hand because we know how to find that. So so it's a sampling distribution. So you do a sample, in things, and you calculate the variance, and you do it again, and you do it again. You record all those. So this is just like the mean concept. You do a sample and you record. Well, what you get in this case is not a normal distribution. This graph, let me look at this thing. That is definitely not a normal distribution. A normal distribution is that. This is not. This is obviously not symmetric. So we're going to go through some aspects of it. So it's not a symmetric graph. Okay, both left and right side tails are tabulated. So you can't just do one side and say, well, that's good enough because the other side is just negative. All right, so both left and right sides, or the tails, are tabulated in the chart. What else? The shaded region represents what? If it's a probability distribution, what does the shaded region have to represent? So the shaded region represents, and you are correct, has to represent probability. So the shaded region always is going to represent probability. And then the total region, total area under the curve, the total area under this curve, if you were to add it all up, what must that be if it's a probability? Probability, and it's a probability distribution, that has to add up to exactly 1. It always adds up to 1 if it's a probability distribution. And so f is the function, as we've mentioned before, very complicated function. I haven't seen it actually. But that's what would give you the curve. It's assumed to be continuous, even though we're dealing with actual discrete values. But if you do enough of them, we're using it as a continuous or continuum when you calculate it. This is the same alpha. Like, so when you say alpha, we mean, significance level of that probability. We will look up these values given degrees of freedom and the calculation, and we'll figure out those probabilities. So if you're in close, well, then you have a huge amount of probability, right? So right in here is most of the information. Being squared, it has to be positive. So that's the other thing. In the book, right there, they used A, but later they used alpha, so we'll just use alpha like that. All right, so let's look at an example. This is going back to chapter 10. Let's read through it. First, a random sample of n equals 25 observations from a normal population, that's one of the stipulations, produce a sample variance of 21.4. Do these data provide sufficient evidence to indicate that the actual variance is greater than 15? Use 0.05 as your test statistic. Okay, we'll do that. All right, so let's do the calculations right here. If you use a formula, always write down the formula. I will copy it because I can. So we're going to copy it. We're going to use that formula right here. Let's write down on the side right there. Let's write down what's given. That's always kind of critical. Let's do the given calculation. I don't know why it's doing that weird color there. That's strange. Just give me some weird funky purple. Nah, okay, we'll just leave it like that. All right, so we're given, what are we given? We're given sample variance, S squared, is equal to 21.4. We're given your alpha level is 0.05. We're given n is equal to 25. Then what do we use in the formula for sigma? Well, we use 15, or sigma squared, that is. So sigma squared is given. And so we don't actually know what it is often. It's just that's what we treat it as the assumption that that's what it is. And then we call it, that's the actual population. So if we're getting sample variances that are a little more, and it's like, is that really a problem? Is it significant or not? That's really the question. You don't want the tolerances of something to be off that much, right? So now we're going to check it. All right, so chi-squared equal 2. Let's do this calculation. And I usually like to write it all out for you the first time. So it's 25 minus 1 times 21.4 over 15. We calculate that. So it's 24 times 21.4. Do the rest in the calculator. Divided by 15. And I get 34.24. What are our degrees of freedom? We'll look that up later in a second. But it's just in -1. So degrees of freedom for this test statistic is 24. All right, so let's state our null hypothesis. A null hypothesis is that sigma squared is 15. Our alternate hypothesis is that sigma squared is greater than 15. So it'll be on the right side, that right side test. So this is a one-tailed test to the right. And we're going to look up chi-squared equal to 34.24. Those are the actual values inside the table, just like your T or your Z. But similar to student T, we have to do degrees of freedom. So with degrees of freedom equal to, which I did above already, is 25 minus 1 is 24. All right, so let's do that. I already have it on the table right here, of course, but at least it gives you nice. So this table's in the back. I decided to copy it directly this time. So you do degrees of freedom is 24. So we go across and we try to find, what was it? 34.24. So you go across, no. It's above this and below this. So it's between those two right there. So we go up, and this is our significance level. Now be careful with that, because which one is bigger? So your p-value is in here, but that's not how you normally write it. So what we have then is our p-value is between 0.05 and 0.1. All right, so if that's the case, do we reject the null hypothesis or not? So if you go to your alpha level, it's right there. It's 36.41. That's larger. Okay, so if you plot it right here for 0.05, that's your alpha level. So it's here. So is 34.24 in the rejection region? And of course it is not. So by p-value or rejection region, and you really want to do both every time to get a feel for it. All right, so therefore, what's our conclusion? Yes, we do not reject H naught. So therefore, let me put that in. Therefore, we fail to reject H naught. The variance is not greater than 15, and this is critical, at an alpha 0.05 level, at an alpha equals 0.05 level. And depending on what you're looking at, that may change. You would reject that at a smaller level. Like if alpha was 0.1, then you would reject the null, because like you can't have that variability. But in this case, it's not a big deal if you're at 0.05. So if you went to 33.196, then that would be over here, and it would be in the rejection region if you use 0.1. So those sort of things often you don't determine. It's determined by the environment you're in, whether you're in medical or you're in engineering or academics. Those levels are determined by the fields you're in, not by yourself as a researcher or a stat student. You just do it. So, okay, that's the idea of chi-squared. Let's continue. And this one's pretty much going to do the whole thing on here. Let's just go through it. This is Pearson's chi-squared statistic, and this is for categorical data, this concept. So the idea for categorical data is it's not a like weights or volumes or things like that. It's for how many people like you know, red apples versus green apples, you know, that kind of thing. Like it's just, that's what we mean by categorical data. It's like you're in categories. So I did an example that's actually a little beyond what the first part of the book does, but it gives a good way, you know, shows you kind of the whole concept. So I'll try to go through it and describe it. This is the idea. These values, so we have two different counties, and they represent the number of people who prefer this color for a sign. I like totally made this up. I actually didn't make up the numbers, but I made up the idea. So County A, they surveyed this many people. So you do the sum. Okay, so you'll do that. Actually, I'll write these down because I'm not going to be able to show you on Excel because it's well, maybe I'll try it afterwards. Okay, so you do the sum, that's 300. These happen to be the same, so it's like they surveyed the same number of people. So this is the row sum. Okay, and these are column sums. This is 260. This would be 250. And this would be 90. We're going to need that for later. So County A prefers, most people prefer blue signs. Again, I just totally made it up, whatever it is. County B, they prefer, looks like red signs, and very few prefer green. Okay, so the null hypothesis is there's no difference in data. Like there's no difference in whether which county likes green or blue versus another. In other words, the counties basically have the same tendency, the same likes for the type of signs they're going to use. Okay, so that's the idea. So the null hypothesis, county and color preferences are independent. There's no association between the counties and the color associations. Okay. Alternate hypothesis, the counties prefer, there is a dependence. Like basically one county likes a certain sign color over the other. Okay. Significance level, that's pretty typical, is a 90, as 95%. That seems reasonable. 90 can be a little low. So 95% gives you most cases. Again, if you get into medical, you don't want people dying, you get into 99% to, you know, release a drug, that kind of thing. All right, so we use the chi-square distribution, and how is it calculated? So it's using a similar concept. These are just a little, this is what the test statistic looks like. It's a little different. You're going to use the sum of O sub I minus, those are observed over expected, minus E sub I squared over E sub I. Your i's go from 1 to k, and your expected case is the probability times the number. So this is like discrete cases. We won't actually have to do that calculation, by the way. I'm just showing you the idea. So where P sub I is a hypothesized probability of each cell, and E sub I n times P sub I is the expected value of each cell. So you can calculate the expected value. Sometimes that'll be given. Sometimes you'll have to do the calculation. O sub I is the O for observed cell count. So that's what you actually found in each cell. Okay, if they are about the same difference, then that'll be small. It'll be a very small number. Okay, then chi-squared will have a small value, and we may conclude there is not a dependence in that case. So if these values are close to each other, the observed versus the expected, then that subtraction is going to give you a small value. That numerator will be then small, and your chi-squared will be small, and it'll be right, like in the middle of that curve. If it's in the middle of that curve, then you're not in those rejection regions. Okay. There's not much. This is called, so this is a two-way classification. Pretty much just follow me on this. I have set up the tables below and I'll talk you through it. And maybe the next video I'll show you how to do the calculation. So you have to calculate the expected frequencies given this table. So suppose you're just given the table. This is how you calculate the expected. What's in there already is the observed. So you do row total times column total over the total of everything. So so this first entry, I can go ahead and start showing you this stuff here. Okay, so that's the example number 1. So here's your sums. So I just entered it in, made it pretty. Your total of everything, 120 plus 150 plus 140 plus 100 is 600, right? Which were just the sum of those. And so then for each entry, you calculate row total. So for this entry, the 130, you calculate the sum, so it'll be 300 divided by 600 is 130. Double check that. So 300 times the 260 over 600. So you do this product divided by the 600. For this entry, same thing. You do the sum times the column sum divided by 600. Okay, so check that out. I've uploaded this in Excel and you can look at it. Okay, so this is your expected frequencies here. And then you do the chi-squared test. So for the chi-squared test, you need to have the this array is your observed, when it'll say it, and this array is your expected. So you have to have those done before you use the chi-squared test in Excel. Other computer packages, you can just kind of give it to it and it'll do it. This is the p-value, which is really small, and therefore was way less than alpha, so we reject a null hypothesis. I said a lot. Okay, so I'm being a little funny there, but it's way less than alpha, so we can reject the null hypothesis. So the null was that there's no difference. Okay, so that they're independent. So the null hypothesis is that it's an independent. The other hypothesis is there's a preference. So there's a preference between the colors. And it turns out, yep, these are a lot different. There's enough difference in them that we can see each county has a different preference. So, I mean, if you look at it, this is 140 versus 150. That's the big deal there. And then this is a big deal here. So what you can do once you have it set up in a computer package is you can test it. So I did. In example 2, I changed the numbers so that they're closer. Right? 120, 140, 150, 120, 40. So these are closer to each other, right? Than the ones above. These are a little farther apart. And then I calculated the expected frequencies by doing row sum times column sum over the table sum. And I did that in Excel. This is an actual formula to do those calculations. Okay, and I get those values. They're all, of course, decimals because it tweaked it. And then this is the chi-squared test when I use this table for the first array and this table for the second. And I forget exactly what it says. You go to chi-squared test, and it's the formula. So you find that in formulas, not the data analysis. It's in formulas. It's CHISQ dot test, and then you do the first one is your observed, and the second one is your expected. and then you hit enter, and it actually only outputs your p-value. Okay, now look at that p-value. That p-value is 0.09. Well, 0.09 is greater than 0.05, so this is not in the rejection region. P-value is not less than 0.05, so we do not reject the null hypothesis. There's no significant difference in the county's preferences. So that's the kind of stuff you can mess with if you have a computer to check it out. And I do have that Excel example in files. So look at that and you can play with it yourself, copy and paste it, and then redo it. So I think that's good enough. Make sure you go through the basic concept, practice a couple in homework, and you'll be good to go.